Welcome everybody to the Association of Space Explorers webinar on defending planet Earth, celebrating Asteroid Day 2021. Asteroid Day is held on June 30th every year to commemorate and help us remember the Tunguska impact of 1908 in Siberia, the largest asteroid impact in recorded history. And we use that event as a milestone in our understanding of the hazard from near-Earth asteroids and what we do together globally to prevent a future damaging asteroid impact. So today, we're joined by some expert panelists with the Association of Space Explorers to tell us about our current efforts to protect the Earth from a damaging collision with a celestial body, an asteroid or a comet. So I'm Tom Jones. I'm a former astronaut, a member of the Association of Space Explorers. I'll be your moderator for today's session. We're going to talk for about 90 minutes total with presentations from our experts from the Lunar and Planetary Institute, from NASA, and from the Johns Hopkins University Applied Physics Lab. And I'll be introducing you to the topic of planetary defense. And this is our celebration of Asteroid Day. Again, Dr. Tom Jones, I'm the chair of the Near-Earth Objects Committee for the Association of Space Explorers, our global organization of space flyers. One of our missions is to preserve our planetary environment and to educate the public about the benefits of space technology. And both of those missions come together as we talk about defending Earth from hazardous asteroids and comets in the coming decade. So our overview for today's session shows me leading off here, talking about defending planet Earth together. On our Asteroid Day panel, we're joined by scientist David Kring. He is the principal scientist at the Lunar and Planetary Institute in Houston and a widely recognized expert on terrestrial and planetary impacts. He'll be talking about Target Earth. And then we're joined by Lindley Johnson and Kelly Fast, both NASA experts on planetary defense. I'll introduce those experts as we go through our session today in more detail. But we have our planetary defense officer in Lindley Johnson and our chief of the observations program for near-Earth objects in Kelly Fast. And then finally, our presentation will be wound up with Lena Adams from the Johns Hopkins University Applied Physics Lab talking about the demo deflection mission called DART. Very interesting example of how we can protect the Earth from an asteroid impact. So I'd like to start off, if I may, by talking about how we can work together to defend Earth from asteroid impacts. As I go through the talk, if you've got questions, please post them in the question and answer feature on the bottom of your Zoom screen, and we'll get to those at the end of the session. So we are faced today with a natural disaster posed by asteroids and comets. When they collide with the Earth, they can strike with tremendous force and cause widespread damage on our planet, as they have many times in the past. And it's a global hazard. The bottom line that I'll get to is that we have to work together to prevent a future damaging asteroid impact on the Earth. The image you see here is of the spectacular near collision with the Earth of the Chelyabinsk asteroid in 2013 over Siberia. Injured over 1,000 people, sent them to the hospital for flying glass injuries, knocked over by the blast, falling furniture and walls. It was a potential catastrophe. Fortunately, this asteroid burst high enough in the atmosphere that it didn't kill anybody on the ground. But it's a hazard that we face continually, and we're going to talk about the details of that, how we can prevent it in the future. I, as an astronaut, flew 4 space shuttle missions, helped build the space station. We space flyers have a particular view of this hazard to our planet. It's very graphic and visceral because of our space experience. And that transfers over to our global fraternity of space flyers. We'd like to promote global cooperation in responding to the asteroid hazard that we face. You'll see the slide again at the end of my talk. It's a learn more slide where you can find more information about the hazard from asteroids and what NASA in particular is doing about that, preventing those future impacts. And you'll see links here that you can refer to at the end of my talk and also at the Association of Space Explorers webpage after the talk is over. So let me start by just mentioning that we are on the 3rd planet out from the sun in this family of 8 big planets and some minor ones as well. Here's a snapshot of the inner solar system. The golden ring around the sun at the center is that of Mercury. The purple ring is Venus. The white ring is the Earth's orbit around the sun. The next planet out, of course, is Mars. And beyond that is the golden orbit of Jupiter near the top third of the screen. You see that big cluster of glowing points between Mars and Jupiter's orbit. That's the asteroid belt. The leftovers of planetary formation, the remnants of the raw materials that went in to form the planets. And sometimes those remnants, which are usually out there in the main asteroid belt and harmless to us on Earth, get kicked into the inner solar system by the influence of Jupiter's gravity and the occasional collision. And those fragments wind up flying through the inner solar system, as you see the white dots that populate the entire inner region of the solar system, Earth's orbit and inward. And so those near-Earth objects composed of asteroids and comets, mostly asteroids, do run into the planets. They fall into the sun, they get ejected by the sun's gravity, but they do run into the planets, including our Earth, and they pose a hazard over the long run to our civilization, as well as life on our world. 65 million years ago, we had a very damaging collision from the object that struck in the Yucatan that wiped out about 75% of life on Earth and altered the course of biology on this planet forever. You know, that's on the large scale. On the small scale, we have debris from asteroids and comets that's naturally falling onto the Earth 100 tons every day. And we had a recent example in May here on the left side of the screen that shows you a collision with a piece of natural debris or perhaps a piece of space junk that struck the robot arm on the International Space Station and left that hole that you see punched into the arm. So if it struck a pressurized area on a spacecraft, that could be a very serious emergency. Astronauts like Ron Garan looking down from the space station have seen countless meteors burning up in the atmosphere below. I remember that very vividly from my 4 space trips. And so the Earth is traveling through a cosmic shooting gallery, as the spacecraft are that surround the Earth. And so we have to be aware of the small scale hazard to small things like spaceships and space stations, as well as to large things like the spaceship we call home, Earth. Now, our nearest neighbor is the moon, our twin planet, if you will. And it's been battered over 4.5 billion years of solar system history by these cosmic collisions, leaving the Earth a scarred and lifeless hulk, leaving the moon a scarred and lifeless hulk. That picture from Apollo 16 graphically shows the craters left behind by these many, many thousands of collisions over the history of the solar system. And down on the surface of the moon, the astronauts on Apollo 17, walked right up to the edge of one of these craters called Shorty Crater, about 100 meters across during their mission there in 1972. The craters are evidence of the violence of the impact process on the Earth. David's going to talk more about that. But these craters are graphic proof that the Earth, flying through space alongside the moon, has been battered just as severely. Our geologically active planet has wiped out most of the crater evidence on Earth, but there are about 190 terrestrial craters discovered that we have evidence for on our own planet's surface that geologists are studying and discovering more of every year. So we are battered as severely as the moon. We just have an active planet that erases a lot of that proof. And in the short span of human history, we haven't seen the planetary scale impacts that you see here. Manicouagan's an excellent example that I've seen from orbit along with my colleagues of an old impact crater about 214 million years old that is about 60 miles across. And this would have had global terrible effects on the biological habitat of Earth. So astronauts see this vivid evidence. We're reminded of it by looking at the moon. We can look down on our own planet and see these scars. And we know that we're in for a future collision with 100% probability unless we as humans do something to prevent that from happening. Now, another way to study craters, aside from going to the moon, is to go to the ones here on Earth, like David and most of my colleagues have done. This is the famous meteor crater in northern Arizona. Astronauts have been training here since the Apollo program back in the 60s. I got to go there with David Kring back in 2011. And you see me with a chunk of that asteroid that survived the impact in Arizona, a large nickel iron fragment of the impactor that created the nearly mile-wide meteor crater in Arizona. So just to give you a quick feel on how I see the asteroid hazard that we face, the near-Earth object hazard that we face from asteroids and comets. There are a lot of small asteroids out there, but only a few big ones that could cause an extinction event on the Earth. Still, those many small ones do present a constant hazard to our civilization. There are about 1 million city killer objects out there, about 20 meters in diameter or larger. If they struck in the wrong place at the wrong time, they could devastate an urban area. We've only discovered 1 or 2% of these so far through our discovery programs. And you'll get Kelly and Lindley to give you an update on the discovery process and progress. Of those objects 140 meters or larger, there are about 25,000 that we think are out there. Only about a third have been cataloged. And those are capable of wiping out an area like the Mid-Atlantic, where I live today. Several states could be destroyed by an impact from an object that size. And among the big objects that present a threat to human civilization, there are about 1,000 of those. And NASA, fortunately, has discovered through its efforts about 95% of those objects. So none of the objects discovered so far in our catalogs are headed for an impact with the Earth, but we're sure to be struck in the future. When we detect one coming, we hope we'll have the skills and the technology to do something about it. How often do these collisions occur? Well, in the case of Chelyabinsk, that impact that occurred over Siberia in 2013, we think those happen about every half century. Fortunately, that one only injured some people. But again, if we have the wrong geometry, a high-speed object, it could penetrate through the atmosphere and destroy a populated area. Tunguska type impact that occurred in 1908, something like 3 to 5 megatons of explosive force. They happen about every millennia, every 1,000 years or so. Objects like the 140-meter class, they could cause regional destruction. Those impact only about every 100,000 years, statistically. We don't have any clear evidence of one of those in the recent past, but of course, we have to be aware of the potential for that destructive energy being released on the Earth and do something about it. For objects that would have global effects 1 kilometer or larger, the ones that NASA has discovered most of, they would strike about every 500,000 years. And you know, the dinosaur killing mass extinction event that could wipe out an entire human civilization, fortunately, they only occur about every 100 million years. And we hope to certainly know enough about the asteroids to ever prevent one of those from coming now that we have space technology and space travel skills. This is just a simple graphic that I really like. I like the colors posed on the map of the Earth here that shows the global hazard presented by asteroids and comets. This is a chart that you'll see from Lindley and Kelly later in detail, but I just want to mention that you can see that the recorded impacts from space-based sensors that the US government runs show how these fireballs from asteroid impacts, small ones, occur all over the planet. The big red circle above Siberia is the Chelyabinsk 2013 impact. So you can see that the entire Earth is confronted with this hazard. It's not limited to any one area on our planet. Now, we had a good example of that kind of global hazard back in 2018 when a very small asteroid, 2018 LA, struck the Earth in the southern hemisphere. And the initial discovery of this asteroid within a couple of days of impact gave us an estimate of where it might strike along the globe. And you see that the initial estimate was all the way from New Guinea to southern Africa, affecting several different nations across the planet. And as that orbit was refined, the prediction of where it would fall was zeroed in on southern Africa, and eventually we did record an impact of this object breaking up in the atmosphere harmlessly over Botswana. And even, as you see in the lower left corner, some meteorite fragments from that impact were recovered. So this is just an example with one of the impacts that we predicted just before its collision with the Earth, where you see that it presents a hazard to several countries before we refine the impact point. And that's a common theme with the initial discovery of a potentially hazardous object. In this hypothetical case, you see the Earth here with the red track of potential impact points from a future collision. Let's say we detect an object and it's going to strike somewhere along that red line. We call that the risk corridor. And we don't initially know perhaps exactly where it's going to fall until we get better information on the object's specific orbit. So you might say that the initial probability is it's going to strike in Colombia in South America. That would be very bad. Now we'd like to do something about that, and we'd like to deflect that object from hitting the Earth at all. So you would want to move that target point off South America and slide it along that red line, either to the upper left or the lower right, so it completely misses the Earth where you see the green crosses there where it would be a good condition. So you initiate some kind of a deflection campaign with a an impactor spacecraft like DART, or with a gravity tractor, or perhaps even a nuclear explosive, and you move the impact point by nudging the asteroid so it misses its appointment with the Earth. Well, if you only move it a little bit, you're going to find that the target point has shifted to either Brazil or maybe to Mexico in this hypothetical example. And those would still be bad conditions. So you want to continue your deflection campaign until you slide that object completely off the Earth and you eliminate the impact risk completely, so that the object will miss the Earth on this pass and never come back to hit us again. And that's what I call a successful deflection. And in order to do that, because many countries are involved, we're going to need an international geopolitical decision to act when we're confronted with an asteroid hazard, potentially hazardous impact. And the way you do that is to enlist the global community, the spacefaring agencies around the world, like NASA, the European Space Agency. We have astronauts from all over the world's space agencies who have flown together and are living together on the space station. All of them are fans of Asteroid Day. We know how we can apply space technology, our space toolbox, if you will, to prevent an asteroid impact if we work together and are prompt in our response. Actually, if we prepare our plans in advance of a damaging impact. I've gone to the United Nations with the Association of Space Explorers and talked to the Committee on the Peaceful Uses of Outer Space, where the topic of planetary defense is a perennial subject, and we've made a lot of progress over the last 20 years. We've suggested bodies be formed like the green and blue boxes, the International Asteroid Warning Network, Space Missions Planning Advisory Group. ASE suggested these bodies to the UN, and with the help of the cooperating space agencies, they put those into reality. And so those work groups are now in existence to help plan our response to a potential impact. And this is a slide from the UN Office of Outer Space Affairs that shows how the International Asteroid Warning Network, the Space Missions Planning Advisory Group, would work together with the UN to advise of a credible threat from an asteroid and develop the mission plans to take care of it. So this process is in pretty good shape. Now we have to put the technical and technology flesh on these bones to make sure that we can prevent a hazardous impact. And we have to do this by search and by mitigation or deflection. First step is to search for hazardous objects with new telescopes like the Rubin telescope down in South America, and the NASA proposed NEAS surveyor mission, which is an infrared telescope, which we'll hear about later, that can detect asteroids far more efficiently than Earth-based facilities. And we want to do demonstrations of our technology. And Lena's going to tell us about the DART mission to demonstrate one form of deflection, kinetic impactors. And we'll hear about that. And it's an international effort, truly, because we've got the European Space Agency contributing the HERA mission to complete the information gain that we'll get from doing the DART flight to Didymos in the coming year. And education is a big part of it. All of you in the audience can participate in Asteroid Day activities like this one, and in 2022 and beyond, to learn more about the asteroid threat and how we can encourage our governments to cooperate together to solve this problem. And exploration is a very exciting element of the solution to the problem of an asteroid impact. We visited the asteroid Ryugu with the Japanese Space Agency in December. That spacecraft returned a terrific sample of the asteroid Ryugu to terrestrial laboratories. And the NASA spacecraft OSIRIS-REx has sampled the asteroid Bennu and is on its way back to give us a look at the rocks and materials from this potentially hazardous object in 2023. Eventually, we can turn this hazard into a big benefit for human space exploration by using asteroids as raw materials for water, rocket fuel, radiation shielding, and metals to build things in space. And we can use the asteroids as intermediate destinations or stepping stones to help us on our way to Mars. Once we get back to the moon, we can go on to the asteroids and then Mars. The bottom line here is that asteroids are a long-term hazard to our civilization, and space exploration is the means to avoid an asteroid catastrophe. You know, we live in the 21st century where we have the tools finally to prevent this natural catastrophe from occurring. And in order to prevent a future impact, we've got to cooperate. We have to look across the globe to work together to employ our space tools and our warning networks to prevent hazardous impact. So that is my presentation. I'm going to step out of my presentation here shortly. Remember, look for the links here that will be posted on the ASE website. So our next speaker is going to be David Kring. David's a principal scientist at the Lunar and Planetary Institute down in Houston. He's a planetary scientist. He's going to tell us about the impact process on planet Earth, target Earth, as I call it. So over to David.
Thank you very much. And thank you again for having me with your group today. I have to say that I've been doing these types of presentations in late June since 1985. At that time, I was a student and I was helping Ursula Marvin with these types of public descriptions of impact hazards at the Harvard-Smithsonian Center for Astrophysics in Cambridge. So I'm glad that we're still doing these types of events. And I want to take a moment to actually point out what's changed since 1985. Since that time, we have seen the impact of Comet Shoemaker-Levy 9 with Jupiter. Up until that point, there were still people in the scientific community who said impact hazards were something that occurred in the geologic past, but it is clearly an ongoing geologic process. We've also had the discovery of the Chicxulub crater and its link to the extinction of dinosaurs and most life on Earth 66 million years ago. As you've already mentioned, Tom, we had the Chelyabinsk impact airburst over Russia in 2013. So we now have, if you will, some blasts from the past to refer to, and I am in the next few minutes going to be summarizing some of those. Okay. So I'm going to start with the Tunguska event, June 30th, 1908. So that's 113 years ago. This blast occurred in a remote part of Siberia, thankfully. But it was so remote that it took scientists many years to actually locate the site and begin a study of that process. The first expedition didn't reach there until 1927. You can see from the picture that I've shown here that it was immediately obvious that the blast had been devastating. One of the key environmental consequences was the forest was knocked down. The trees were just blown over, littering the Earth's surface as you see here. And that is characteristic of the smaller, more common types of asteroid impact events. As I'll say repeatedly, I think today, there is this impact air blast. And here you can see a map illustrating the consequences of the Tunguska air blast. You see there's an arrow that illustrates the trajectory of this incoming object. There is a ballistic shock wave as it enters the atmosphere, and then there's a final blast shock wave at the point of detonation. And collectively, those blast effects knock down the forest in what is oftentimes described as a butterfly pattern, seen here in yellow. Over 2,000 square kilometers of the forest were blown down by those blast effects, and the energy, I should say, of that blast was actually detected around the world. Now, more recently, we had another impact event in the Northern Hemisphere. This one occurred over Russia. In February 15th, 2013, we had a small asteroid about 20 meters in diameter hitting the Earth at 40,000 miles per hour and with a kinetic energy of 500 kilotons. And here are two illustrations of that impact event. There is a picture that was captured as it went through the Earth's atmosphere. And in a little panel towards the top left, you see a computer simulation that Mark Boslow did of this impact event. And you can see it penetrating the Earth's atmosphere. And with that white expanding line, you can see the consequences of the shock wave and the air blast that it generated radiating along that trajectory. The shock wave and air blast caused damage in the nearby town of Chelyabinsk, hence the name Chelyabinsk. Here you can see that it blew out windows in one of the town's buildings. Here you can see a plume of smoke rising from a factory that was created when the wall of the factory collapsed due to the shock wave and air blast. Here is a picture of that same factory wall after the smoke is cleared. And here is a close-up view of that wall and the rubble that littered the sidewalk. Fortunately, in this particular location, nobody was walking on the sidewalk when the building wall collapsed, and so there was no local injury here, although, as I'll show in the next slide, there were injuries throughout the area. So let me say a little bit more about the components of this impact air blast, because it really is an essential component of these small asteroid impacts. And let me begin with the shock waves. Shock waves are produced by objects moving faster than the speed of sound, that is faster than Mach 1. Impacting near-Earth asteroids penetrate the atmosphere with a speed equal to or in excess of 11.2 kilometers per second. That's Earth's escape velocity, which is more than 25,000 miles per hour, which is more than Mach 35. And that produces a ballistic shock wave as it penetrates the atmosphere. The Chelyabinsk near-Earth asteroid was moving at Mach 60 to 61. There's a second explosive shock wave that is produced when the object catastrophically fragments in the atmosphere, or if it hits the surface to produce an impact crater. And those shock waves, which are large pressure deviations, produce high velocity winds, which we call these air blasts. And this phenomenon, by the way, is something that we witnessed during the Cold War around nuclear explosion test sites. Here is a map that shows the distribution of damage created by the shock wave and air blast around Chelyabinsk. The darker gray zone there in the core represents where the most damage occurred, and the lighter gray zone on the margins are where there was little to no damage. But as Tom already noted, over 1,600 people were injured and requested medical care following this impact airburst, and more than 7,000 buildings in the region were damaged. Now, this particular impacting asteroid came in at a shallow 16-degree trajectory, and modeling by Mark Boslow said the very same size asteroid, if it had come in at a steeper angle, would have caused even more damage. Now, in this particular case, we actually have relics of the impacting asteroid that produced the Chelyabinsk air blast. This is a picture of one of those relics. You can see that it is what geologists will call a breccia. That is, the rock, which is basically a white colored rock, is cross-cut by all of these black veins or veinlets. And those actually are produced by impact events that modified or damaged the asteroid long before it hit the Earth. And so this asteroid was weakened before it collided with the Earth. That is, it had a lower structural integrity, which make it more likely to explode catastrophically in the atmosphere as opposed to on the ground. Now, it's actually a common thing for asteroids to be damaged. They spent 4.5 billion years evolving in the asteroid belt, and they've had a lot of opportunity to bump into each other. In some cases, those collisions just form small craters on larger asteroids. Sometimes those collisions can completely disrupt a body, and then the material can reaccrete into a rubble pile. In either case, those types of collisions can weaken the asteroid prior to its collisional course with Earth. Now, because we have samples of the Chelyabinsk asteroid, we can actually link it to other existing asteroids in the asteroid belt or on near-Earth trajectories. And one of those asteroids similar to the Chelyabinsk meteorites is the Itokawa asteroid. This is an LL-type asteroid. This particular asteroid was visited by Japan's Hayabusa spacecraft. And you can see the scale of the asteroid compared to the International Space Station, where Tom has visited, and the new Orion crew vehicle, which is being built for our astronauts who are going to explore the moon. Here is a close-up view of Itokawa. And you can see that it has a boulder-strewn surface, obviously a structurally weak object. And I put a red circle around one of the boulders that's 20 meters in size and comparable to the object that actually produced the Chelyabinsk airburst. Now, larger asteroids near-Earth objects, and stronger asteroids can actually penetrate the Earth's surface, the Earth's atmosphere, and reach the Earth's surface where they can detonate catastrophically and excavate an impact crater. And the world-class example of this phenomenon is METEOR crater in northern Arizona, also called the Barringer meteorite crater. This particular crater was produced by an asteroid that had the kinetic energy of 10 to 15 megatons of energy, a tremendous burst. It excavated a bowl-shaped crater here that you can see about 1.2 kilometers across. And I have to say, if you have an interest in this subject and you want to see the consequences of an asteroid impact event, I urge you to travel to northern Arizona to see METEOR crater. It's just a few miles outside of Flagstaff. It's in the vicinity of the Petrified Forest in the Grand Canyon. So it's very easy to slip into your vacation travel plans to the American Southwest. I mentioned that this was a 10 to 15 million megaton blast. That's about 28 times more energetic than the Chelyabinsk impact event. And like Chelyabinsk and Tunguska before it, the shock wave and air blast were two of the most important environmental effects of this impact event. The blast effect was immediately, and actually to illustrate that, I have here a satellite view of METEOR crater, and around METEOR crater, I have a series of black circles that represent limits to specific types of damage. I'm going to walk you through that damage in the next few slides. The blast effect was immediately lethal for human-sized animals within the inner 6-kilometer diameter black circle. Severe lung damage would occur within the next 10 to 12 kilometer diameter circle due to a pressure pulse alone, and animals would be severely injured and unlikely to survive within those distances. Winds would exceed 1,500 kilometers per hour within that inner circle. Here in Houston, we're worried about hurricane force winds at 150 miles per hour. So 1,500 kilometers per hour just absolutely dwarfs that. Winds would still exceed 100 kilometers per hour at radial distances of 25 kilometers, which is that third black circle that you see depicted there. And the outermost 50-kilometer circle represents the outer limit of severe to moderate damage to trees. That is also sufficient to damage human structures of comparable strength if they existed in that region. Now, this particular impact event occurred 50,000 years ago, and so the fauna that suffered the consequences of this were ice age animals like mammoths and mastodons. But years ago, I pointed out that the very same size impact event, if it were to occur over the United States today, over a modern urban area such as Kansas City, it had the capacity to damage buildings and injure people, if not kill them, throughout the entire metro area, as you see depicted here in the lower right panel. Now, the granddaddy of them all, of all impact events, is the Chicxulub impact event that occurred 66 million years ago, which extinguished dinosaurs and most life on Earth that existed at that time. Over 75% of the species that lived on Earth, both on land and in the seas, perished. And it also produced a shock wave and air blast. And so to illustrate the scale of that is a map here. You see within that red circle that the severe air blast flattened forest over an area that covers most of Mexico as it exists today. And that yellow circle outlines the limits of gale to hurricane force winds that you can see penetrated most of southern North America. Now, as devastating as those the shockwave and air blast was around this impact event, it's important to point out that as you go up in scale, as you go to impact events larger than Tunguska, Chelyabinsk, and METEOR crater, you begin to get regional and global consequences. And those environmental consequences are shifts in climate, globally distributed wildfires, just a whole host of environmental consequences that create extinction level events. That certainly is what the Chicxulub impact event was 66 million years ago. Now here's a final slide with just a few final thoughts. Fortunately for us, extinction level impact events like Chicxulub are far less common than small impact events like Chelyabinsk and Tunguska. Those are the Chelyabinsk and Tunguska events are the more common ones. And fortunately, again, for us, the atmosphere is a wonderful shield. In the case of Tunguska and Chelyabinsk, the objects detonated in the Earth's atmosphere. It took an object the size of a meteor crater and a strong iron meteorite, in that case, to actually reach the ground. But larger fragments, like that produced a meteor crater, do exist and can breach that shield and can cause havoc at Earth's surface. So we have to be mindful of that entire suite of objects in near Earth space as we look forward to preventing such impact events and such devastation in the future.
Thanks. And I'd just like to ask, David, what recent impact events beyond the time horizon of Tunguska are you aware of? You know, obviously they're smaller than the very damaging impacts like the Yucatan Chicxulub impact, but any events that have happened in the last few tens of thousands of years beyond Meteor Crater that you can point to that are of really great scientific interest today?
Well, I think that Meteor Crater in northern Arizona is the type example. It's the one that we've studied the most and deserves additional study. But I have to say that our understanding of impact events, small and large, based on our studies of the Earth, are limited because the Earth is such a dynamic geologic planet. And so, as you pointed out, we only have about 200 impact sites preserved on the Earth. And so teasing apart the environmental consequences of some of those impact events is a tremendous challenge. And this, of course, you've allowed me to segue into one of my favorite comments when we talk about impact hazards, is that the moon, only 3 days away, is a wonderful place to better understand impact processes. There, the record is exquisitely preserved. We have over 300,000 meteor crater size impact craters or larger. And so if you actually want to understand the geologic processes associated with those collisions, we really are driven to go back to the lunar surface. And not only can we see the consequences of young impact events on the lunar surface, in fact, occurring annually, we can actually detect impact flashes occurring annually on the lunar surface. But because the moon has been geologically stable, with the exception of impact cratering for 4 billion years, we can actually see the collisional evolution of the early Earth when life was first evolving on our planet, exquisitely preserved on the moon. And so we really do need to explore the lunar surface to better understand the collisional processes that have shaped Earth history.
Fantastic. And we look forward to getting that evidence back in here within a few years from some human explorers and following in the robots path that are up there right now. So speaking of NASA efforts to get back to the moon, let's talk to our NASA experts now from the Planetary Defense Coordination Office at NASA. We've got the Planetary Defense Officer, Lindley Johnson, who's been a friend of mine, along with Kelly Fast for many years in this planetary defense effort. Kelly is the program officer for all the near object observations programs that NASA runs. And they're going to do a tag team approach here, telling us about NASA's current and future efforts in planetary defense. So over to Lindley and Kelly. Thank you for being here.
Going okay here. So yeah, Kelly and I basically manage the planetary defense program that NASA has. And just to be clear of what we're talking about here, near Earth objects, those are asteroids and comets that come into the inner solar system, and we need to detect those and track their orbits because we want to find the ones that are potentially hazardous to the Earth. In other words, come within this ring around Earth's orbit. But the only way you can do that is by finding everything that's coming here into the inner solar system and then projecting, getting enough observations to project those orbits out in time to see which ones are going to approach the Earth over time, and also characterize them to understand if they're large enough to really do damage at the Earth's surface if they were to impact. And a prime example of a near-Earth asteroid is the asteroid Bennu, which is the recent destination of the OSIRIS-REx mission, and collected samples this last year, and now it's on its way back to Earth with those samples to allow us to understand these near-Earth asteroids a lot better. NASA's Planetary Defense Coordination Office, we've been in existence a little over 5 years now. Well, in short, our job is to make sure that David doesn't have any more craters on the Earth to study. Our work is to detect any potential significant impact, be able to, through modeling and our understanding of the characteristics of asteroids and how they may penetrate Earth's atmosphere, as David was talking about, be able to assess what the potential effects could be of any potential impact, and then develop the strategies to prevent those impacts, or at least lessen the effects on human welfare. This slide shows all of the sectors that we work in to do this. And of course, the first thing we got to do is find them. So a good part of our program is the search and detect and tracking of these objects that come within the Earth's vicinity. Then we have a good many projects that are busy characterizing those objects, their size, composition, so we may know better what we're dealing with. The word coordination in our name is very important, because also a lot of what we do is coordinate our activities, both in finding and characterizing these objects, but also in determining what we might do about one if it were found on an impact trajectory with the Earth. So coordinating both within the institutions within the United States and the other U.S. government agencies, and also internationally. So you see a good deal of our effort is involved there. And of course, the area that all the Hollywood movies are about is mitigation. What do we do about it if we find one on an impact trajectory? So we're have projects working that both to, if we had to take an impact, what would we do about it on the ground, working with the emergency response community, FEMA in the United States. But if we find them far enough ahead of time, which is really our goal, how could we deflect an asteroid in space? And you'll hear about our DART project. So our current guidance as to what trying to improve our capabilities here comes out of the National Near-Earth Object Preparedness Strategy and Action Plan. This is actually a plan that's been started work on back in 2015. The strategy part was released in 2016, and then the action plan was added in June of 2018 for this final document, which you can find at that link. So this is a work that has crossed administrations and is very well supported. It is the plan for how do we improve our capabilities over the next 10 years. And so it talks about how do we enhance our detection, characterization, and tracking capabilities. There's a lot of modeling and prediction involved in determining if there's going to be an impact and what the effects might be. So improving those models and how we do those predictions and how we integrate all that information so we can inform both decision makers and the public. Then, of course, develop technologies that we can do deflection or disruption out in space. Increasing the international cooperation on NEO preparation, as Tom mentioned in his introductory presentation, And then working to improve our impact emergency procedures and protocols within the U.S. Government. So turn it over to Kelly now to talk about the Near Earth Object Observations Program.
Right, the first order of business in planetary defense is finding the NEOs. You can't do anything about them unless you find them. And NASA's program actually goes back a number of years, back to 1998. So this work has been going on a long time, even though it's more recently been formalized into the Planetary Defense Coordination Office. And the NASA Authorization Act of 2005 set the current objectives. There was an amendment to NASA's Space Act in order to make this sort of work, NEO detection, tracking, and research, one of the purposes of NASA. So NASA is supposed to be doing this. And in the current goal, NASA has been directed to find and catalog 90% of the near-Earth objects greater than 140 meters in size within 15 years, that is by 2020, which is known as the George E. Brown Near-Earth Object Survey Act. And we have not reached that yet, but you're going to hear today about ways to accelerate the survey to get to that point. But our current survey systems that have been working very hard, racking up the discoveries as fast as they can. The major surveys are the Catalina Sky Survey at the University of Arizona and the Pan-STARRS survey at the University of Hawaii, and they're producing the bulk of the discoveries of near-Earth asteroids. But there's other components that contribute quite a bit. The ATLAS telescopes, which are designed to maybe find objects that might not have been caught by the other surveys because they have to spend longer times on patches of the sky, to maybe as a last alert system. There's also sites being developed in Chile and South Africa for ATLAS, which is primarily in Hawaii right now. There's partnership with the Space Force on their Space Surveillance Telescope that has been recently deployed in Australia. And we work with the Linear project at MIT Lincoln Labs that pulls the natural object discoveries out of the data from this telescope. There's Caltech's Wiki Transient Facility, which this program funds to also pull the asteroids out of their survey data, since that's not their primary objective. And there's the NEOWISE mission, which is a repurposed space telescope. It was the Wide Infrared Survey Explorer. It was an astrophysics mission, but it was picking up the asteroids also. And when that mission, excuse me, are actively cooled and cannot be cooled anymore because of the cryogen was used up, but the remaining channels were used to detect asteroids in the infrared, producing more characterization data on sizes than discoveries, but contributing to this whole package of telescopes here working to discover asteroids, catalog them, know where they're going to be in the future. And a big part of that is the Minor Planet Center, which is the internationally recognized repository for small body measurements from position measurements from all around the world, which is funded by NASA's program. And so position measurements are sent to the Minor Planet Center from around the world. And the Minor Planet Center does the preliminary orbit determination, and they also handle the naming and the designation of these objects. But also the Center for Near-Earth Object Studies at the Jet Propulsion Laboratory uses those position measurements to do the real precise orbit determination, both in the short term for objects that maybe haven't even been confirmed to be new discoveries yet, just to see is there anything that poses a short-term threat, and then also long-term, out 100 years, to see if there's an object that poses a threat in the future. And in the event of an identified impact, CNEOS determines the time, location, and geometry of that event. But planetary defense is a team sport, and it does involve agencies and observers and science institutes, universities all around the world. And they have collaborated together in two groups that were recommended by the United Nations Committee on the Peaceful Uses of Outer Space. And these two UN recommended groups are the International Asteroid Warning Network, or IAWN, which pulls together observers and modeling institutes and universities and space agencies that have the capability to observe or model asteroid positions and properties. And right now that is coordinated by NASA. And they've had observing campaigns together and exercises to try to make sure that the communication is good on this sort of activity, so that that's the case if that's ever more critical. And then there's also the Space Mission Planning Advisory Group, or SAME page, which is a collaboration of space-capable nations to look at possibilities for deflection should an impact threat be discovered. And then this group would recommend to its bodies what missions might be possible. And then countries around the world would make the decisions using some of that input. And that body, SAME page, is chaired by ESA. And so going back to IAWN, International Asteroid Warning Network, to give you an idea of how many are involved, I mean, I think I need to update this slide again. We've got 32 or more signatories, and all of NASA's program is just wrapped up in what's listed there for NASA, similarly for ESA. And then you see a lot of other agencies or independent astronomers, universities, just contributing their assets toward this effort to the extent that they do in their own countries or in their own organizations, but at least opening that lines of communication to collaborate on the asteroid impact hazard. Next slide. And these bodies, IAWN and SAME page, do report out to the United Nations once a year. This was from an earlier report. But when the Scientific and Technical Subcommittee meets in Vienna, Austria, as part of UN COPIS, these bodies do report out on progress during the past year of these collaborations of both observers and the idea of planning missions. And so where are we right now? These are the stats that are available on the Center for Near Earth Object Studies website. And not too long ago, we busted through the 26,000 number for the number of near Earth asteroids. And so even further than what we have here. And so you see the plot over time here with NASA's program really getting going in 1998. And so racking up the asteroid discoveries, the red represents 1 kilometer and larger, the really large asteroids. It's leveled off because a lot of that population, as Tom mentioned, has been identified. The smaller ranges, like the 140 meters and larger, like we said, that Georgie Brown survey number is in yellow, and that's still ramping up. We have not, we've found a lot of those objects, but still have a ways to go. And then as you go smaller and smaller, there are more and more of those asteroids. And so that's represented in the blue. And so in this, you can see the different size ranges. But to give you an idea of how things have been going over time, these bars represent the number of discoveries every year along this plot by the different surveys, like Pan-STARRS in pink, Catalina Sky Survey in green, the recent big producers. And you'll see that in 2020, actually, this is really impressive, despite COVID, that they actually set a record in total discoveries. There are reasons for that, with working very hard to set up safe operating plans so that they could continue their operations. And then also in some observatories, some maintenance wasn't done because of COVID, and so they continued observing. So this was impressive, though. There was also not a lot of, there wasn't really a monsoon season in Arizona, so that contributed. And so continuing to rack up discoveries in 2021. But in the next slide, as you see for the, just the asteroids that are 140 meters and larger, that Georgie Brown survey, things have really leveled off for the past number of years, just meaning that we've kind of hit the limits of our capabilities for that size range. We really need to wait for, as we go around on the Earth, like kind of around the racetrack, around the sun, and the asteroids are going around the racetrack, around the sun, kind of have to wait for the asteroids to come back around for us to find them because of the limitations of our capabilities. And so new capabilities are needed in order to accelerate this and punch through some of these kind of plateaued numbers that we've seen in recent years, but still looking and finding as many as we can detect with the capabilities we have. Next slide. I'll pass it back over to Lindley.
Okay, well, looking at this goal that we have directed by Congress of finding the 140 meter and larger, the total population of that size and larger is estimated to be about 25,000. And this pie chart shows where we are in completing that work. And you see that there's still about 60%, a little over 60% left to find. Most of them, of course, smaller than 300 meters in size, but there's still many that are in the hundreds of meters in size. And so we need to keep looking for those as well. So how are we going to catch up with this and get this done in a time period that is less than 30 years, which is what it would take to complete at our current rate of finding these objects? And the answer to that is our new mission, the NEO surveillance mission and the Near-Earth Object Surveyor spacecraft that has just recently been approved to go into its preliminary design phase. It is designed specifically to find these near-Earth objects. And with 5 years of operations, we believe we'll be well past 65% of the currently undiscovered potentially hazardous asteroids. And it will achieve that 90% goal, working with other assets, our ground-based assets, and things like the Rubin telescope that was mentioned earlier, to achieve completion of the George E. Brown goal. And another important capability here, and why we're looking in the infrared, is with the observations that are taken in the infrared, we can get the size, a good size estimate directly from the same observations that we take to discover and track these objects. We don't have to have a completely separate program to do those kinds of things. Of course, all the data will be delivered into the same public databases that are currently being used. And the other good news that we just got in June is that the President's budget request for the next fiscal year, FY22, will fully fund the NEO Surveyor project for launch in 2026, provided it's enacted by Congress. So it's in Congress court now. So why are we looking in the infrared? Well, here you see two asteroids of the same size, one very reflective and the other one quite dark. And if you look at them, the visible, the dark one is hardly can be seen. But in the infrared, because it is absorbing the Earth's sunlight and then re-radiating it in the infrared, that heat in the infrared, the size, the area that's re-radiating is the same size. So they look the same in the infrared, have the same bright signature against the background stars. The other thing about the NEO Surveyor and B design, we talked about NEOWISE earlier. This is its field of regard. This is what it can see of the sky at any one day. And so it takes it 6 months as it goes around with the Earth in the solar system to do one complete survey of the sky. The NEO Surveyor will be positioned at the Earth's Sun L1 point, and the area that it will look both in front of the Earth in the near-Earth orbit and behind the Earth is represented here. It will survey all this area in a month, 2 weeks worth looking ahead of the Earth and 2 weeks looking behind the Earth, and repeat that pattern continuously as it goes around with the Earth in this L1 gravity stable point. So back to you, Kelly, and talk about our characterization work.
Right, real quick, in addition to finding them, you want to know something about asteroid properties, because if one does ever pose an impact threat, you want to be able to characterize that, what type of threat, and that could be based on what an asteroid is made of. Is it very metallic, or is it kind of very rocky, fluffy? Our primary characterization asset on the ground is NASA's Infrared Telescope Facility, which does all kinds of observations of objects or of targets, astrophysics, planetary science, supporting NASA missions, but also for near-Earth asteroids. And I'd shown earlier that the needle in the haystack, surveys try to find them, wide swaths of the sky. Telescopes like the Infrared Telescope Facility narrow down on a particular object and try to discover properties, like through spectroscopy, looking at the spectrum of light coming back from an object, shown like here on the right, to try to infer some of the properties of the asteroid. And a fantastic way to study like the properties of an asteroid shape and rotation and nailing down the orbit is through radar. The asteroid has to come close enough. It's not something like at the airport where the radar sweeps around and picks up the airplanes. You don't have that kind of power. But if it is known exactly where an asteroid is, and if it's close enough to the Earth to bounce radar off of it, you can get some amazing properties. Goldstone is the primary radar right now in California. That has been returned to full power last year. The other primary radar that used to be was the planetary radar at Arecibo Observatory, and tragically, support cables broke and ultimately decommissioned the telescope. And so that was one of the most sensitive planetary radar capability. And so it's unfortunate to have lost that, and so continue to look at future capabilities. But Goldstone does continue to operate now at full power. And when you do have asteroids that are close enough that you can bounce radar off them, you can get fantastic radar imagery to see things like satellites, moons of asteroids in the lower left, or bilobed structure. But continuing on, after getting those shapes and sizes of asteroids, we kind of have there's a case that Tom mentioned earlier, this asteroid 2018 LA. And so just really quickly to add some detail to that, this was an asteroid, one of 3 that had been discovered prior to impact. To actually see it coming and to be able to make predictions about it, was discovered by the Catalina Sky Survey in Arizona. It was found to be less than 3 meters in size. Nothing that would cause an impact threat. As David said, the atmosphere does a fantastic job of taking care of these small objects. You get a pretty fireball. So no reason to warn or notify about it. It was discovered 8 hours prior to impact because it was small, and there were additional observations that contributed. And so the Minor Planet Center and JPL Center for Near Earth Object Studies warned the Planetary Defense Coordination Office of potential impact. And then CNEOs calculated the impact corridors with available data. You saw the initial corridor from Tom there on the left. And then on the right, when additional data was added from the Atlas telescopes, that narrowed that impact corridor down to just over Southern Africa. And that really narrowed things down. And then sure enough, at the right time, bolide was detected over Botswana by government sensors, with the right duration. And even a surveillance camera picked this up, and you'll be able to see the asteroid coming into the atmosphere and disrupting. It doesn't really impact the surface because it's just over the horizon there. Atmosphere took care of it, pretty fireball. And then finally, after the impact later on, first of all, this was also detected by other means. There are government sensors that the map that was shown earlier by Tom picked up the fireball. So there's 2018 LA. You can see it was one of the smaller ones that gets picked up by the sensors, but still it's an amazing exercise to get to do this from discovery through even detections by Comprehensive Testband Treaty Organization infrasound sensors. So lots of things coming into play with this exercise. And then finally, as Tom mentioned, there were meteorites recovered from this object. And meteorites are recovered all the time on the ground, but it's an amazing thing to recover a meteorite from an object that was observed in space, to which you can track an orbit back and where it came from. So also just from planetary defense activities, there's a lot of fantastic asteroid science that comes out of it. So this was a really neat exercise of the whole system, and so that if this is ever needed, things are in place. Next slide.
Yeah, in total, there were some 25 meteorites collected from this fall, about 25 kilograms of material, pre-sample material of cosmic material.
Right, yes.
So over the time that we have been working with other agency partners on this in the last 30 years or so, the number of impacts that have been of smaller asteroids in Earth's atmosphere is 866 as of middle of May, as you see here. Tom showed this slide earlier. The scale over on the right side, the energy release equivalent to the Hiroshima device. I mean, I hate to compare these natural events to nuclear weapons, but that is the type of, that's the closest type of energy that we know of that has the same effects in blast that a asteroid impact would have. And so at that level, the orange color, those are equivalent or larger than the Hiroshima device. And then we have a couple of events, as was talked about by David. Chelyabinsk was about 20 times the Hiroshima explosion. And then we also had an event in the Bering Sea in late 2018 that was about 3 or 4 times the energy release of Hiroshima. In total, there's about 30 events that have been recorded over the last 30 years that were Hiroshima or larger in size. All this information, though, is collected and understand it is important to our modeling and our asteroid threat assessment work. And as David talked about, the determining what the air blast might be from an impact, as well as effects that might be felt on the ground, both impact if it's large enough or thermal effects, is part of our asteroid threat assessment project, so that we can appraise what effects might be from a impactor that we found, and know how bad it might be. And so modeling of the asteroid itself, its characteristics, what will happen as it enters the Earth's atmosphere, the entry physics, simulating the thermodynamics, ablation, and radiation modeling, and then the blast effects simulations, and if it's large enough, what kind of crater will it make, or if it lands in the ocean, what kind of tsunami might result. To do a probabilistic risk assessment and provide to the decision makers, the White House and the emergency response community in the U.S., and the similar kind of information provided with our partners around the world. Here in the last...
This last topic is a great segue into Lena's talk, so let's move on to hers.
Right, exactly. Our move through it quite fast here, so but a few words about it. We've studied mitigation techniques for several years now, and a study back about 10 years now said we had about 3 technologies that could be used to deflect. All of them are based on the principle of changing the orbit velocity of the asteroid just a little bit, months to years in advance, and of course then that will change the orbit of the asteroid and make what was going to be a hit a complete miss. Now, if time is short and the object is large, then a nuclear device may be our only option. But the key to our program is finding these objects well in advance so that we have time to do something about them in space. Kinetic impact deflection, if we have about 10 years of warning, could be quite effective for what the most frequent sized object we might face. And then there's also what we call a gravity tractor if we have even greater time. And the nice thing about it is it's controllable. An enhanced gravity tractor that goes down and picks up a boulder off the surface to enhance its mass. Then you use nature's tug rope, the mutual attraction with a station-keeping spacecraft with tons of mass in its arms to slowly tug the asteroid off of the trajectory. The Hollywood solution, which we wouldn't do it the way they do in Hollywood, which tries to blow the asteroid to smithereens. Now, the real way to use a nuclear explosive device is for it to be a standoff detonation that irradiates the surface on that side of the asteroid and causes it to blow off from the heat and heating up the gas and material. And then, of course, there's an opposite reaction on the trajectory of the asteroid. And finally, kinetic impactor. double asteroid redirection test, and our project systems engineer, Elena, is going to tell you all about that.
Very good. Thank you very much, both Kelly and Lindley, for that thorough overview of the NASA Planetary Defense Program. And it of course, is sponsoring the Double Asteroid Redirection Test, DART. And our next speaker is Lena Adams, who's the DART Mission Systems Engineer. She's basically the technical lead for the DART mission. So she's going to tell us about this kinetic impactor demonstration. So over to Lena. Tell us about DART.
Welcome. I'm the DART Mission System Engineer, which means I'm the technical lead responsible for all of the technical aspects of the DART mission. And I'll talk to you about our mission, about our asteroid that we're going to, why are we going there, when are we getting there, and where we are in process of actually arriving there. So we'll start with, of course, we don't work this is a team sport, as both Kelly and Lindley have mentioned. This is a large team. We are an international team. Not only do we have lots of folks across the country, most of it is done at the Johns Hopkins Applied Physics Laboratory, but we have a lot of folks across the country, participation with all of the NASA centers, as well as the Italian Space Agency, who are providing a CubeSat that's going to go along with DART. And we have a large international investigation team. So this is DART in a nutshell, in one slide. Our goal is pretty simple: try to get a binary asteroid system called Didymos. It consists of two asteroids, Didymos and Dimorphos, and I'll talk about those in a couple of minutes. We are launching in November this year, and we have a pretty large launch period for a planetary mission. From November to February. We're going to launch in a SpaceX Falcon 9 rocket. And once we're launched, we spend about 10 months in commissioning. We're bringing a little CubeSat with us from the Italian Space Agency. And our goal is to impact the moon of this binary asteroid system, so called Dimorphos. And after we impact, LiCHA is going to fly by and take some images of the impact crater and the ejector, the plume of stuff that's going to come off of the asteroid that we created. So a little bit, and after that, as our NASA program scientists like to say, the real mission starts, at which point the Earth observatories are going to observe how much we change the period of the moon around the main asteroid. And that's what we're going to do for a couple of months and see what impact we have, right? So this is a basic physics problem. The kinetic impact is we have a DART spacecraft that is about 600 kilos, and it's going to impact the Dimorphos asteroid at 15,000 miles an hour. It's going to change the orbit by very little, right? So the orbital period of Dimorphos around the Didymos asteroid is only, it's about 12 hours, 11.92 hours. And we're changing it only by 10 minutes at most. That requirement is actually only 73 seconds. And we should be able to detect that from Earth. So we're doing this when Dimorphos is really close to Earth. Dimorphos and Didymos, they're both are potentially hazardous asteroid, PHAs, which means they're coming pretty close to Earth. And but this is an incredibly safe and controlled experiment because we're not changing the orbit of our main asteroid, Didymos. What we're doing is we're just changing the orbit of the moon around the main asteroid. So the main asteroid is still going to go around the sun like it always has. And what we're doing is we're just speeding up slightly the Dimorphos's rotation. So in terms of scale for, how big is this asteroid that we're going to? So Didymos is about 780 meters. There's of course always some uncertainties with those sizes as well, but it's somewhere between Burj Khalifa and the World Trade Center. And Dimorphos, the asteroid that we're trying to actually hit, is 163 meters. And that's about the size of the, somewhere in the Great Pyramid of Giza kind of size. So or 2 football fields, however you'd like to think about it, 0.1 mile. So if you think about it, it's actually a really hard problem to hit an asteroid, because here you are at Earth and you're aiming for something that is 0.1 miles from about 6.8 million miles away. And how do you do that when you don't even know how the asteroid looks like? That is one of the challenges that DART has. So the DART itself is shown on the left there, and it's a small spacecraft, about 2 by 2 meters, but its wingspan is actually pretty large, about 19 meters. So back to what will DART do? You know, what are our level 1 requirements? What are our objectives? What are we trying to accomplish here with DART? So for a lot of the science missions, you have much more detailed science objectives, but DART is very straightforward because we are a technology demonstrator. We have to go impact Dimorphos. We need to, when Dimorphos is actually close to Earth, so we can observe it afterwards from our telescopes and from radar. We need to change its binary orbital period. And as I said, we need to cause a 73-second change. We need to be able to measure from Earth that change in the period, and then also measure just how much we have enhanced its movement by hitting the asteroid and creating the ejecta that's going to come out. So something that Lindley showed just a couple of minutes ago when he was talking about a nuclear explosion, where you basically have an asteroid, and if you detonate something right by the asteroid, you will blow off some of the stuff on the surface. And that is going to act as a thruster or create an ejecta and actually, as a reaction force, propel the asteroid forward. So we're doing the same thing, except with a kinetic impactor, where we impact the asteroid and we're able to possibly speed it up because this ejecta is going to come off and act as a thruster. So just to show you a quick movie of this is Dimorphos and this is Didymos doing its rotation. And of course, Didymos is about a 1.5 kilometer away from Dimorphos. We are trying to hit it when it's as far away from Dimorphos as possible, because it's easier to see where it is. And we impact it, and then the Leachy cube just fly by, and then we change the orbit in such a way that now the orbit is actually smaller. So, you know, if you're wondering how much do we change in orbits, it's very little. I mean, the asteroid itself rotates around the bigger moon by about 17 centimeters per second. So it's very slow. And we're changing it, you know, so it's rotating around the bigger moon about 0.4 miles an hour. And when DART impacts, and we're going pretty fast, we're going at 15,000 miles an hour, we're impacted. And even though with all of that impact, we only change it by about 0.001 miles an hour. So it's not that much of a change, however, measurable. So how are we going to measure it afterwards? So what you're seeing here is as the Dimorphos rotates, we are sitting on Earth, and what we're watching below is the brightness of the asteroid over time. So you can see that there are strategic dips as Dimorphos actually passes in front of Didymos. The brightness dips. So that's how we know that the asteroid has passed, and we can measure how much the actual orbit period has changed. So of course, we have a lot of partners who have signed on to do these observations, and many of those folks Kelly already mentioned that are part of the NEAS network. But in addition to that, investigation team was able to secure lots of telescopes to observe this. So how much do we expect to move the asteroid? And it really depends. It depends on what the asteroid is actually made out of. We do not know, just like probably in real life, although, you know, we might have some characterization data of the asteroid, just like in real life right now, we have no idea what this asteroid is made out of. There are theories, but how much we'll be able to, by hitting it, change the momentum of the asteroid, it really depends if it's a rubble pile or how much porosity there is in the asteroid, or if it's a metal chunk, right? And depending on what kind it is, you might be able to move it farther, faster, or not. In addition to being the first kinetic impactor demonstrator, we also are carrying a lot of and demonstrating a lot of other new technologies for NASA. And they start with, of course, is how we actually getting to the asteroid. We're using a special technique called autonomous smart navigation. And for the last 4 hours, the spacecraft is completely autonomous. And all of that is accomplished using our imager called the Draco telescope and our autonomous navigation SmartNav together with our special avionics, where we do a lot of processing all on the spacecraft. And the spacecraft is doing everything by itself. All we're doing from the ground is receiving images of the asteroid as we're getting closer to it. Of course, we can intervene if needed, but all of it is going to be autonomous. We are also demonstrating some new types of solar arrays and a new type of ion engine as well. So this is just a picture of our spacecraft, just because you can see that we have our Draco imager on the bottom of the spacecraft. We have our new rollout solar arrays that are really long, that are powering our Next-C engine that's hidden by this cover. But most of our control is just done by hydrogen thrusters. But the key here is that, we have this special imager on top in our spacecraft that is actually going to be the eyes of the whole thing and be able to image the asteroid and guide us to the asteroid as well. So it's a visible imager. It is a narrow angle camera, and in a sense, it's a narrow angle that, let's say I'm in DC and the camera is in New York. On the camera field of view, I would be 2 pixels. So it's pretty, you can look pretty far away. And we're able to detect the asteroid, the main asteroid, the 780-meter asteroid, about 30 days before we hit. And it's really important to have this camera and all of these other technologies like autonomous navigation is because we know very little about Dimorphos and Didymos and about this whole object that we're going to hit. So on the left, you're seeing a movie of Didymos moving through the sky. This is from an observation in 2019. Last time Didymos came closest to Earth was in 2003. When we got a lot of observation using a radar and we're able to come up with a shape of that asteroid really looks like. However, we really don't know what Dimorphos, the asteroid that we're trying to hit, really looks like. Is it a perfect sphere? That would be nice. But most likely the small asteroids are not perfect spheres, nor are they perfect ovals. They have rugged shapes, and figuring out how do you find that shape, and most likely part of it is going to be shaded and part of it is going to be lighter because the sun is hitting it. Finding that shape, finding that right angle to hit the asteroid is all part of this mission. So, and the problem is that we are not going to know what it looks like until we hit it. This is just kind of an image of what happens in the last 4 hours. So in the first 4 hours is just 1 pixel for our asteroid. Then about 60 minutes out, the size of Didymos, the main asteroid, is about 6 pixels. And finally, about an hour out, we're starting to see Dimorphos, and it's just 1 pixel to us, nothing else. And it's not until we're pretty much done maneuvering. So the spacecraft has to be taking images of the asteroid, maneuvering, sending images back to Earth, doing all of that while it's trying to guide itself into a pixel on this field of view of the camera. And so about 4 minutes out, you can see this image of just where you're up to about 21 pixels just in the field of view. So pretty much nothing. And really, you don't meet your requirements of trying to image the asteroid until about 20 seconds out. So we're sending images 1 per second, pretty much streaming video back to Earth, and then we hit. So it is a very exciting time in the last couple of minutes. But before then, it's a lot like watching paint dry with just 1 pixel. So it's been quite a hard year this year. We had to do lots of things, of course, via Zoom, as you can see from the investigation team meeting, but it's hard to do that and build the spacecraft at the same time. For the spacecraft, we had to come in, and in fact, March last year was when our integration readiness review have happened. But since then, we have come in, we have built up the whole spacecraft, we have tested it quite a bit. We installed a lot of our new technology onto the spacecraft and started on a lot of our environmental testing. You can see it going into thermal vacuum. Installed our solar arrays and installed our Draco imager onto the spacecraft, which at this point, we are going to be ready for launch in November. We're moving to the Vandenberg Air Force Base, launching from there, separating from the launch vehicle. One of the first things we do is, we roll out our solar arrays, just because this is a new demonstration of the rollout of the solar arrays that are on ISS. Open up the door of our imager, make sure that we can see that asteroid, and then 9 months later, we catch up with it. Yeah, so last 30 days are really exciting. We are getting ready. We're opening up our doors. We're releasing the Leachy cube. We're seeing that one pixel, that's the asteroid. And that's always really fun. So, and then once we detect the Didymos system in a little bit more color, we zero in our target, and I hope you stay tuned for next year in October. Next year, we're going to hit. So coming to the theater next to you. Thank you.
Very interesting, Lena. Thank you very much for that update on DART. It's something to really look forward to this coming year and next. We have one question about DART that just came in for the DART mission. How do we know if it's going to hit along the center of gravity line? If it's just off a little, much of the kinetic energy will go into rotational change, perhaps, or not into changing its orbital period. That's from Mike Helton.
Yeah, so most of it still will go into the asteroid, and you also will get ejected back, which will enhance that ability to move the asteroid forward. We have done a lot of the simulations for that, and we're finding that even if we hit a little bit off center, we're still good. But that's one of the goals, is to actually hit within 15 meters of the center of the asteroid. Now, if you think about 15 meters, it's not very much from 6.5 million miles. So it's been quite challenging, I'll just say, to get your spacecraft to actually hit that.
Oh, thanks. When will we know the launch date? When do you think we'll zero in on a particular day?
So our launch date right now is November 24th, and we're getting to be ready for November 24th. So if the launch range is ready, we're going to be ready.
Yeah, you have to get me a ticket into Vandenberg. I hope the viewing area can be opened up to the public by then. So,
apparently very foggy.
It's actually late night on the 23rd at Vandy, so you got to plan on being there on the 23rd.
Okay, I'll make a point of that.
Yeah, it's the 24th.
1 in the morning Eastern.
Yeah.
And it's a very long launch sequence.
Well, it's quite exciting. I wish you all the best, and our thanks to your team for putting this mission together. We're excited to see the results, and of course, it's just one way that we could deflect an asteroid. You've all mentioned in your discussions various other methods. The nuclear explosive. There's the gravity tractor, very elegant. You don't have to touch the asteroid at all. And one that's been getting a lot of attention of late has been ion beam deflection, where you spray the asteroid with the exhaust from an ion thruster over a sustained period of months. And that impact of those tiny little ionized nuclei will have enough momentum to shift the orbit of an asteroid as well. So that would be
I mean, that's certainly a viable technology for the future, but that's technology that still has to undergo some development.
You bet. Yeah, so there's lots to go forward with. And, Lindley and Kelly, what would you think would be the next step beyond the surveillance mission from space? Once you get that space-based surveillance platform to detect the asteroids, what would you like to see coming along down the pipeline after that, if you have a personal favorite? In terms of a demo mission to help us generate an effective planetary defense toolbox.
Well, while we're still in the situation we are and looking for them, one of the things is that a potential impactor might be, found going to impact us in the next few years. And so one of the capabilities we need is rapid reconnaissance of that object. We need to be able to get a spacecraft out there to take a good look at it so we know what we're dealing with. Now, this could be very, capabilities are in the range of a small satellite. It doesn't have to be a big, OSIRIS-REx sized capability. So I think the next step that we would try to take is demonstrate a fast response, rapid reconnaissance capability. And we have a very good upcoming opportunity to do that with the close approach of Apophis in 2029. And so looking at demonstration of some rapid response spacecraft to go meet Apophis on its way in would be something that would be good for improving our program's capabilities.
I've got a quick question for Kelly, and that's we lost the radar at Arecibo, and that's a vital capability. What do you see as a way to recover from that?
Well, at least, as I said, we still also have the Goldstone radar, which was more steerable than Arecibo, but didn't have the sensitivity that Arecibo had. And so it's not like we don't have a capability, but Arecibo was an important capability to have. And there are some other less capable radar efforts that are kind of getting spun up, but there are possibilities maybe for looking to the future as a partnership with other agencies that also would have an interest in such capability. And actually there's workshops going on to that effect. The National Science Foundation just held a workshop, and there have been other workshops looking at future radar capabilities that would maybe not try to recreate the technologies of the past, but try to look at possible future technologies or rather more modern technologies like phased array radars rather than single monolithic dishes. So it's still ongoing, but at least we still do have radar capability, which is important.
Yeah, David, what's your latest field project? In terms
Drop out there.
Who dropped out? Can you hear me, David?
Yes, I can hear you fine.
I dropped out. I mentioned that we are in work with partners, National Science Foundation and the U.S. Space Force about what a potential future deep space capability might be.
Okay, that came through loud and clear, Lindley. Thank you. Thanks for adding that. So I just was going to ask David, what's your latest field project that you're looking forward to, and what's the area of impact studies that excites you the most? I think you mentioned the moon, perhaps something that's closer to home that you might be able to get to in the next few years.
Well, closer to home is what's riveting our attention is still the Chicxulub impact crater, linked to extinction of dinosaurs and most life on Earth. And just a couple of years ago, the International Ocean Discovery Program and International Continental Scientific Drilling Program gave us the funds to drill into the crater. It is the world's biggest and best preserved impact basin on Earth, but it's buried. And so we have, it's a little bit expensive to collect samples from the crater, but we did recover a beautiful core. Phenomenal core. It far exceeded our highest expectations. And so we're going through that core to better understand the crater forming process, how rock actually flows. Rock flows in an impact crater when it's being formed. Understand the impact generated hydrothermal system. It actually modifies a vast region of the Earth's crust. And the intriguing thing about Chicxulub is not only did it extinguish life, but it became a cradle of life. Life began to reoccupy the crater faster than other parts of the world. And part of that has to do with the impact generated hydrothermal system. And not only is that exciting for events 66 million years ago, but it's actually our best proxy for the biggest basin forming events during early Earth history. And so we've detected a microbial ecosystem in this post-impact hydrothermal system that is a model for hopefully, or we think, a potential model for the origin of life on early Earth over 4 billion years ago. And so that's exciting, not only to the geologists, but to the biologists, the astrobiologists. And so it is a really fascinating cross-cutting study.
Great, great. Well, that's just another fascinating area that we can open up next year when we visit again for another asteroid day. So we look forward to getting smarter about asteroids, both in space with Lena's work, from the ground with the observation programs that Kelly runs, through our international partnerships across the globe, where Lindley's heavily involved with cooperating with other space agencies. And I'm personally excited to hear about the latest from terrestrial and lunar impact studies as we get our hands on the evidence of these past destructive impacts to teach us how to prevent future ones. So thanks all of you for contributing today. And I'll look forward to continuing this discussion in the weeks and months ahead. And I'll see you out at the launch site at Vandenberg, Lena. Okay. So that wraps it up for the Association of Space Explorers. We thank you for tuning in to our Asteroid Day Defending Planet Earth session. Thanks for coming, and we look forward to more dialogue with you in the days and weeks to come. So long.